We know the moon is shrinking by looking at the lobate scarps in detail. They actually reflect the crustal materials of the moon being pushed together, breaking, and being thrust over one another.
Scientists are shaking. China cracked open a sealed container of moon soil and found something so impossible, so deeply strange, that researchers could not explain it. A dead world with no atmosphere, no chemistry, and no life had been secretly manufacturing one of the most expensive materials on Earth.
What's exciting about these findings for me is that the moon is not a dead body. It's not an object where everything that happened on the moon happened billions of years ago. These scarps could be younger than a billion years. They could be, in fact, as young as a couple of 100 million years old, or they could be even younger than that. And that means, in geologic terms, the moon is active.
For billions of years, in complete silence. Nobody knew. Nobody even suspected. And that is not even the most shocking part. What else was hiding inside that soil has rewritten everything we thought we knew about the moon. And nobody is talking about it. Somewhere in a research laboratory, scientists are working with one of the most extraordinary materials ever studied. It is made entirely of carbon, arranged in a flat sheet just one atom thick. It is roughly 200 times stronger than steel, nearly weightless, and conducts electricity better than almost anything else known to science. It's called graphene, and producing even a small quantity of it on Earth requires carefully controlled, laboratory conditions, specialist equipment, and considerable expense. A single gram can cost thousands of dollars depending on the quality and the method used to make it. For decades, researchers have been refining the processes needed to manufacture graphene reliably. Some methods involve chemical vapor deposition, where gases are broken down at high temperatures and carbon atoms are deposited onto a surface in thin layers. Others use chemical or mechanical techniques to strip layers from graphite one at a time. None of these approaches are simple, and none of them are cheap. The material sits at the center of countless research programs because of what it could eventually make possible, from faster electronics to lighter aircraft structures to more efficient energy storage. The problem has always been making enough of it, at a price that makes it practical. In June 2024, a team of Chinese researchers opened a sealed container of soil collected from the moon and found graphene, already there, formed naturally without any human involvement at all. That finding alone was enough to change the way scientists think about the lunar surface. But it was only one part of what came back from a mission that had taken years to plan and which came closer to failure than most people will ever know. The Chang'e 6 mission was designed and operated by the China National Space Administration. Its goal was specific and ambitious: to land a spacecraft on the far side of the moon, collect samples from one of the oldest and deepest impact craters in the entire solar system, and return those samples to Earth. No mission had ever done this before. Several had tried to reach the far side and failed at various stages. The difficulty is not just technical, it is geographical, in a sense that applies even in space. The far side of the moon is the hemisphere that permanently faces away from Earth. Because the moon rotates at the same rate as it orbits, the same face is always pointed toward us. The other side is never visible from the ground, not even partially. This means that any spacecraft attempting to land there loses direct contact with Earth the moment it passes behind the moon. Radio signals travel in straight lines. They cannot pass through 3,400 kilometers of rock. To solve this problem, China launched a relay satellite called Queqiao 2 in advance of the mission. The name translates roughly as Magpie Bridge, taken from a Chinese folk story about two stars separated by the Milky Way and reunited once a year by a bridge of birds. The satellite was placed in an orbit that allowed it to maintain line-of-sight contact with both Earth and the lunar far side at the same time, acting as a signal repeater between mission control and the spacecraft. It was an essential part of the mission architecture, and without it, the landing could not have been attempted at all. Even with the relay satellite in place, there were limits to what ground controllers could do once the landing sequence began. The time it takes for a signal to travel from Earth to the moon and back is roughly 2.5 seconds at minimum. During a fast, dynamic landing sequence, that delay is enough to make real-time control essentially impossible. commands sent from the ground would arrive too late to respond to conditions that had already changed. The spacecraft had to be capable of making its own decisions. The flight control team, led by mission director Zhang Hailian, had spent years preparing for this. Every system had been tested repeatedly. Failure scenarios had been rehearsed. Terrain maps of the landing zone had been built from orbital imagery gathered in advance. The onboard guidance software had been programmed with hazard avoidance capabilities that would allow it to assess the surface in real time and adjust its approach accordingly. The team had done everything within their power to prepare the machine for what it would face. But when the lander began its final descent in May 2024, the control room could do nothing but monitor the data as it came through, delayed and fragmented, and waited. The target landing site was the South Pole Aitken Basin, located near the southern pole of the lunar far side. It is one of the largest and oldest impact craters known to exist in the solar system. The basin stretches approximately 2,500 kilometers across and reaches depths of around 8 kilometers below the surrounding terrain. It was formed more than 4 billion years ago when an object of considerable size struck the early moon with enough force to excavate material from deep within the lunar interior. Scientists wanted access to that material precisely because it had not been significantly altered since the moon's earliest period. Collecting samples from this location would allow researchers to study conditions that existed in the inner solar system before Earth had developed any of the features we recognize today. The problem was that the same ancient violence that made the basin scientifically valuable also made it physically hostile. The floor and surrounding terrain were littered with boulders, uneven slopes, and overlapping craters from billions of years of subsequent impacts. The approach zone contained hazards that orbital cameras could identify but not fully map at the resolution needed to guarantee a safe touchdown. The lander's sensors would have to do that work in real time during the descent itself. As the spacecraft dropped through the final kilometers of altitude, its guidance system was continuously scanning the surface below. It was comparing live imagery against preloaded hazard maps, identifying safe zones, rejecting areas that posed a risk, and adjusting its trajectory accordingly. Thrust levels changed, the angle of approach shifted. All of this happened automatically, without input from the ground, while fuel was being consumed and the pull of lunar gravity was drawing the vehicle downward. The landing legs made contact with the surface of the South Pole Aitken Basin, and confirmation reached the control room shortly afterward, delayed by the distance and the relay path. The spacecraft was stable. The mission had reached its first critical milestone. Zhang and his team had spent 6 years working toward a moment that lasted 15 minutes of complete uncertainty, and they had come through it. The lander remained on the surface for approximately 2 days, collecting material from the regolith using a drill and a scoop mechanism. Around 1.9 kilograms of soil and rock were gathered and sealed into a return capsule mounted on an ascent vehicle. The ascent vehicle then launched from the surface, rendezvoused with an orbiting module, and began the journey back to Earth. 53 days after the landing, the return capsule entered the atmosphere and landed in Inner Mongolia. The samples were transferred to research facilities, and scientists began the work of finding out what had actually come back. What they found in that soil was not what anyone had expected. When the returned samples were brought into the laboratory, the first thing researchers noticed was the color. The soil was darker than expected. Scientists familiar with lunar material had a reference point for comparison. The samples brought back by the Apollo missions decades earlier were pale and grey, resembling fine ash or powdered concrete. The material from the South Pole Aitken Basin did not match that description. It was noticeably darker, and that difference, subtle as it might seem to a casual observer, was the first indication that something genuinely unusual had come back from the far side. To understand why that matters, it helps to look at the moon from a distance. The surface visible from Earth is not uniform. There are bright regions and dark regions, and the contrast between them has been observed and recorded for as long as humans have studied the sky. The dark patches are called Maria, a Latin word meaning seas, a name given to them centuries ago by astronomers who mistakenly believed they might contain water. They do not. What they contain is ancient solidified lava, the remnants of volcanic eruptions that took place billions of years ago. When molten rock pushed up through the lunar crust and spread across the surface, it cooled into smooth, flat plains that reflect less sunlight than the surrounding highlands. That lower reflectivity is what makes them appear dark. The near side of the Moon, the face that always points toward Earth, is covered with these dark volcanic plains. They are a defining feature of the lunar landscape as seen from our planet. The far side is strikingly different. It has almost no maria. Instead, it is brighter and more heavily cratered, with a rougher surface texture that suggests a very different geological history. Scientists had observed and documented this asymmetry for decades, but explaining it convincingly required evidence that had not yet been collected. Chang'e 6 provided that evidence. The samples showed that the two hemispheres of the Moon did not develop in the same way. The near side, it turns out, contains higher concentrations of radioactive elements within its interior. These elements generate heat as they decay, and over geological timescales, that heat had a significant effect on the structure of the crust above. The near side crust remained thinner, around 60 kilometers in places, and the heat generated beneath it kept the underlying mantle material more fluid for longer. This allowed magma to push upward and break through the surface repeatedly, flooding large areas with lava and creating the dark plains that are visible today. The far side followed a different path. Its crust grew considerably thicker, reaching depths of around 80 kilometers in some regions. The interior cooled more rapidly and to lower temperatures. Without the same heat source driving volcanic activity from below, magma could not break through that thicker lid. The lava never reached the surface in the same volume. No dark plains formed. The far side preserved its ancient cratered terrain largely unchanged, while the near side was repeatedly resurfaced by volcanic floods that erased much of the original landscape. This means the Moon has been carrying two distinct geological personalities within a single body for approximately 4 billion years. The difference is not a matter of gradual variation across the surface. It is a fundamental split in the internal structure and thermal history of each hemisphere, and it answers a question that had remained open in planetary science for a long time. The Chang'e 6 samples did not just add detail to an existing theory, they provided the direct physical evidence needed to confirm it. That finding alone would have made the mission significant, but the examination of the returned soil continued, and what came next was considerably harder to explain. Under high-powered microscopes, researchers found structures within the lunar dust that had no straightforward explanation. Wrapped around individual mineral grains in layers measuring just 2 to 7 atoms in thickness were sheets of graphene. The same material that research laboratories on Earth spend enormous resources trying to produce had formed naturally in the lunar soil, without any of the conditions that scientists consider necessary for its creation. Graphene does not form easily. On Earth, its production requires either carefully controlled high-temperature chemical processes or painstaking mechanical separation of atomic layers from graphite. The Moon has none of the infrastructure that makes either of those approaches possible. It has no atmosphere, which rules out any chemistry involving gases. It has no liquid water, no biological activity, no industrial processes of any kind. It is a cold, airless, radiation-exposed surface that has been geologically inactive for billions of years. There is no conventional scientific framework that would predict graphene forming there spontaneously. The explanation that researchers arrived at involves the one process that the lunar surface experiences constantly and in enormous quantities: impact. The Moon receives a continuous bombardment of micrometeoroids, particles ranging from microscopic dust to small fragments, traveling at speeds of tens of thousands of kilometers per hour. Earth's atmosphere slows and burns up most of this material before it reaches the ground. The Moon has no such protection. Every particle that approaches the surface hits it at full velocity. When a micrometeoroid strikes the lunar regolith, the collision releases a concentrated burst of pressure and heat at the point of impact. For a fraction of a second, the conditions at that microscopic contact point are extreme enough to alter the structure of the material involved. Carbon atoms already present in the soil are subjected to intense compressive force and high temperatures. They are pushed into new arrangements, forming the layered crystalline structure that defines graphene. The cooling process happens almost instantaneously in the vacuum of space, which locks that structure permanently in place before it can break down. The Moon has been running this process continuously for billions of years across its entire surface, impact after impact, accumulating graphene in the soil with no particular intention and no awareness of what it was doing. The material that humanity has invested decades of research and significant financial resources into producing in controlled environments has been assembling itself in lunar dust through the most straightforward mechanism imaginable. Things hitting other things very hard. The implications of this extend beyond scientific curiosity. Graphene is considered one of the most promising engineering materials currently known. Its combination of strength, low weight, and electrical conductivity makes it theoretically useful across a wide range of applications, from structural components in spacecraft to protective coatings for surfaces exposed to radiation to conductive elements in electronics and energy systems. The challenge has always been producing it in sufficient quantities at a manageable cost. If the lunar regolith contains graphene that can be extracted and processed, the surface of the Moon becomes a potential source of material that would otherwise require expensive manufacturing on Earth. The third major finding from the Chang'e 6 samples addressed something that had long been considered one of the fundamental facts about the Moon: that it is dry. The reasoning behind this assumption is straightforward and well supported by the history of lunar science. The Moon formed from the debris thrown into orbit when a Mars-sized object collided with the early Earth more than 4 billion years ago. The energy released by that collision was immense. The material that eventually gathered into the Moon passed through a molten state in which temperatures were high enough to vaporize any volatile compounds, including water. By the time the Moon had solidified, it should have lost essentially all of its water content. The samples brought back by Chang'e 6 suggested the reality is more complicated. Researchers found water molecules trapped inside small glass beads present in the returned soil. These beads form when impact events melt surface material, which then cools rapidly into glassy spheres. Solar wind, the stream of charged particles flowing outward from the sun, carries hydrogen atoms that can interact with oxygen in the glass as the beads form or cool. The result is water molecules locked inside a sealed glass structure protected from the vacuum and radiation of the lunar environment. Separately, researchers identified hydrated minerals in the samples, crystalline structures in which water molecules are incorporated directly into the atomic lattice of the host mineral itself. This water is not sitting loosely on the surface where it could easily be lost. It is chemically bound within the mineral structure, held in place by the same forces that hold the crystal together. Studies examining this type of water storage across the lunar surface suggest the total quantity involved could be very large, with some estimates reaching into the hundreds of trillions of kilograms when extrapolated across the entire Moon. The significance of this for any future human presence on the Moon is considerable. Water is not just something people need to drink, it is a source of oxygen when split into its component elements, and the hydrogen it contains is a potential rocket propellant. Every kilogram of water that can be sourced from the lunar surface is a kilogram that does not need to be launched from Earth at extraordinary cost. If the extraction technology can be developed to process water from glass beads and hydrated minerals in a vacuum environment, the economics of a sustained human presence on the Moon shift substantially. The barrier is no longer whether the resource exists. The question becomes whether it can be accessed efficiently. 3 distinct findings, each one significant on its own, all contained within less than 2 kilograms of ancient dust collected from a single location on the lunar far side. The Moon that emerged from the analysis of those samples was not the familiar dead rock of popular imagination. It was a world with a complex internal history, a surface continuously transformed by the physics of impact, and resources distributed through its soil that no one had fully appreciated before. The containers holding the Chang'e 6 samples arrived at research facilities in China in the summer of 2024. What was inside them amounted to approximately 1.9 kilograms of material, a modest weight by any ordinary measure, but representing something that no laboratory on Earth had ever held before. These were the first samples ever collected from the far side of the Moon, drawn from one of the oldest geological formations in the solar system. And they carried within them a record of events stretching back to a time before Earth had stable continents, before life had emerged, before the inner solar system had settled into anything resembling its current arrangement. The scientific process of analyzing returned space samples is slow and methodical by necessity. The material is irreplaceable. There is no option to go back and collect more if a sample is damaged or contaminated. Every gram is handled with extreme care, divided among research teams, stored under controlled conditions, and examined using techniques that range from standard microscopy to highly specialized spectroscopic analysis. The findings that emerged from the Chang'e 6 material did not arrive all at once. They accumulated over months as different research groups worked through their portions and published their results. What those results described, taken together, was a moon considerably more complex and more resource-rich than the one that had existed in scientific thinking before the mission. The three central discoveries, the geological split between the two hemispheres, the natural formation of graphene in the lunar soil, and the presence of water stored in glass beads and hydrated minerals, each addressed a different aspect of what the moon is and what it might eventually mean for human activity in space. Individually, any one of them would have justified the considerable cost and effort of the mission. Together, they represent a shift in how planetary scientists understand the lunar surface and what it contains. The asymmetry between the near and far sides of the moon had been observed since spacecraft first photographed the far side in the late 1950s. Soviet and American missions documented the difference in appearance, and subsequent orbital surveys mapped it in increasing detail. Theoretical explanations had been proposed over the years, most of them centered on differences in the internal heat distribution of the early moon and the way those differences affected volcanic activity over time. But a theory supported only by remote sensing data is always incomplete. Direct physical samples provide a different category of evidence. They allow researchers to measure the actual chemical and mineral composition of the material to date when different processes occurred, and to test theoretical models against real-world results rather than observations made from a distance. The Chang'e 6 samples confirmed that the internal thermal history of the two hemispheres genuinely diverged at an early stage, producing the geological contrast that has been visible from orbit for decades. That confirmation matters not just for what it says about the moon, but for what it suggests about how planetary bodies in general can develop differently within a single object. The moon is relatively small. The fact that such significant internal variation could develop and persist across billions of years in a body of that size has implications for how scientists interpret data from other moons and rocky planets throughout the solar system. The graphene discovery introduced a different kind of significance. The formation of graphene through micrometeoroid impact is a process that, once identified on the moon, raises immediate questions about where else it might be occurring. The moon is not the only airless rocky body in the solar system subjected to continuous bombardment. Mars has a thin atmosphere, but its surface is struck by considerably more impactors than Earth's. The moons of other planets, asteroids, and smaller bodies throughout the solar system experience the same physics at varying intensities. If impact-driven graphene formation is confirmed as a reliable natural process, the lunar finding may be the first documented example of something that is widespread across the solar system, producing complex carbon structures in environments that were previously assumed to be chemically inert. For the practical question of what the moon could provide to future missions and eventual permanent installations, the graphene finding is one part of a larger picture that the Chang'e 6 results help to clarify. The traditional view of the lunar surface as a resource environment focused primarily on what could be found in permanently shadowed craters near the poles, where water ice was thought to have accumulated over billions of years, delivered by comets and asteroids, and preserved by the permanent cold of areas that never receive sunlight. That picture has not been replaced by the new findings, but it has been significantly expanded. The water stored in glass beads and hydrated minerals is distributed across the surface, not confined to polar craters. This means it is potentially accessible from a much wider range of landing sites than the polar ice model would suggest. The extraction process is different, requiring heat to release water vapor from glass or minerals rather than simply excavating and melting ice. But the underlying principle is the same. Energy is applied, water is released, and the resulting vapor is captured and processed. The engineering challenges involved are real, but they are not fundamentally different from challenges that industrial processes on Earth have solved in other contexts. What was missing before was certainty that the resource existed in sufficient quantities and in accessible forms. The Chang'e 6 results moved that question considerably closer to a definitive answer. The broader context for all of this is a period in which multiple national space agencies and private organizations are actively planning sustained human presence on and around the moon. NASA's Artemis program has the stated goal of returning humans to the lunar surface and establishing infrastructure for longer-term operations. the European Space Agency, has contributed to these plans and has its own lunar science priorities. China's space program has outlined a roadmap that includes crewed lunar missions and the development of a research station on the lunar surface, with Russia listed as a partner in that effort. Several private companies are developing lunar landers and surface systems as commercial ventures. The Moon is, by any reasonable assessment, about to receive considerably more human attention than it has at any point since the Apollo program ended in the early 1970s. In that context, what the Chang'e 6 mission demonstrated extends beyond the scientific content of its samples. It showed that the far side of the Moon, which has been the most inaccessible part of the nearest world to Earth, can be reached with current technology. The relay satellite architecture that made the landing possible is replicable and expandable. A single Queqiao satellite provided enough communications coverage to support one mission, A. Constellation of such satellites could provide continuous coverage of the entire far side, making it as accessible for surface operations as any point on the near side. The infrastructure needed to open the far side to regular exploration is not speculative. The basic version of it already exists. The South Pole Aitken Basin, where Chang'e 6 landed, is of particular interest for future missions beyond the single visit that has now taken place. Its age means that material from the lunar interior, excavated by the original impact event more than 4 billion years ago, is exposed at or near the surface across a vast area. Studying that material systematically could provide a record of the Moon's early geological evolution that no other location on the lunar surface can match. The 1.9 kilograms returned by Chang'e 6 represent a tiny fraction of what the basin contains. Future missions returning larger sample masses, or eventually supporting human researchers working directly at the site, could build on those initial findings in ways that are difficult to predict in detail, but clearly substantial in potential. There is also a dimension to the Chang'e 6 results that sits outside the immediate scientific and practical questions, and that concerns what the mission represents in terms of where lunar exploration stands as a whole. The Apollo missions of the late 1960s and early 1970s transformed human understanding of the Moon and produced a generation of scientific work that is still being built upon today. When that program ended, the Moon receded from the center of human space activity for half a century. The samples collected by Apollo, 12 in total across 6 landings, all came from the near side. The far side remained unvisited by any mission capable of returning material to Earth until Chang'e 6 changed that. The findings from those samples have demonstrated that the near side samples, comprehensive as they were, represented only part of the picture. The Moon that the Apollo astronauts explored was geologically distinct from the far side in ways that are now measurable and documented. A full understanding of the Moon as a planetary body requires data from both hemispheres, and that data is now beginning to arrive. The 4 billion years during which the far side accumulated its geological record in isolation were not, it turns out, years of simple inactivity. The crust thickened. The interior cooled along a different path than the hemisphere facing Earth. Impacts continued at the same rate as everywhere else on the Moon, and those impacts were doing something at the atomic scale that no one suspected until the samples came back. The surface was building complex carbon structures. It was storing water in forms that can survive for geological timescales in a vacuum. It was preserving a record of the solar system's earliest period in mineral compositions that have remained essentially unchanged since the Moon was young. None of this was visible from orbit. None of it could be deduced from telescope observations or remote sensing data alone. It required physically going there, collecting material, and bringing it back for analysis. That is what Chang'e 6 did, and the results have changed the scientific understanding of the Moon in ways that will take years to fully work through. What they have already established is that the far side was never simply the back of a dead rock. It was a place where the physics and chemistry of the solar system had been quietly at work for a very long time, producing things that matter, waiting for someone to finally arrive and look closely enough to notice.